Hello, I'm Erwick.
I'm Shadaab.
I'm Gopinath.
We're the team from NIT Trichy and we present to you a project, the Auto Balancing Bike.
A lot of modern day objects are inspired from things seen in movies. For example, the mobile phone was invented by a guy who first saw the science fiction series Star Trek.
Likewise, the inspiration for our project came from the movie Dark Knight, or more specifically, a vehicle within the movie, the Batpod. The Batpod is shown to feature doing a lot of stunts and moves that are unconventional to two-wheeled vehicles.
So we wondered whether we could replicate these stunts using real-world physics, mechanics and electronics.
Now, let's take a look at the mechanical assemblies that went into this project. The frame that we have used is made out of aluminum, steel and plastic. This is to allow for a stable and well-balanced platform to implement the balancing mechanism. The vehicle's unique design includes a two-wheel drive configuration to enable distribution of power to both wheels instead of one. The wheels are driven each by a high-capacity brushless outrunner motor that grips the inside of the wheel that causes it to spin. The motor's diameter is considerably smaller than that of the inside of the wheel. The torque generated is considerable enough for the relatively small motor to drive the vehicle. The wheel mounts are made up of steel sheets attached together with the help of aluminum L channels to form a U-shaped mount that holds the wheel in place. A motor is mounted to the inside of the mount that spins the wheel. The rear wheel mount is bolted securely onto the frame. The front wheel, on the other hand, is free to rotate about its steering axis, but without wobble. The balancing arms are mounted on the interior of the main body of the vehicle. Counterweights are attached to the tips of these arms in order to make them more effective as balancing arms. Stoppers are attached to the tips of the servo arms and the holes are drilled onto the balancing arms. The servo arms' central positions are locked at 45 degrees from the center in order to allow for maximum throw. As the vehicle tilts to one side, the arm extends to the opposite side in order to return the vehicle to its central position above the roll axis. The steering mechanism consists of the wheel clamp assembly, which includes the wheel, steering column that is attached to the clamp, and the rocking arms that are attached to the column. All three move as one unit. The assembly is mounted to the front of the vehicle. The steering servo controls the steering assembly via bicycle brake wires that are stretched taut in their housings in order to prevent the assembly of moving independently of the servo's movements. The steering mechanism is very unique in the sense that the steering actuator, or more specifically the servo, is located away from the steering column in order to be able to alter the torque supplied to the steering column. This obviously is not possible if the steering servo were attached directly above the column. If this was done, further problems would include bulkiness of the steering assembly. The vibrations generated by the motors, wheel and assemblies are sufficient enough to disturb the sensitive readings taken in by the IMU sensors. Therefore, we have implemented working shock absorbers into our vehicle that absorb vibrations and shakes with respect to their positions.
The electronics involved were a challenge to come up with as well. A Spectrum 6-channel transmitter paired with its own receiver is used to steer the vehicle remotely. The motors used are 1300 rpm per volt brushless outrunner motors. These are paired to an electronic speed controller that governs the speed of the motor according to the pulse width modulated signals transmitted via the receiver. The motor grips the inside of the wheel that causes it to spin. The motor's diameter is considerably smaller than that of the inside of the wheel. The torque generated is considerable enough for the relatively small motor to drive the vehicle. One of the buck converters is TPS54428, which is responsible for stepping down 11.1 volts from the battery to about 6 volts for the purpose of operating the servos. At this particular voltage, the servos have maximum torque output, which facilitate easier operation of the arms. A PCB is made for using the small outline package. The second buck converter used is TPS51220 evaluation module for the purpose of obtaining 3.3 volts from 11.1 volts. This powers the microcontroller, the Bluetooth module, and the sensor hub. The buck converters are chosen over normal linear regulators since they are much more efficient in stepping down and produce negligible heat during the process. The batteries used are lithium polymer, which are capable of sourcing currents as high as 40 amperes. The battery has a splitter for the purpose of powering one of the wheels, the electronic speed controller, and the buck converters. The electronic speed controller also powers the receiver, which is responsible for controlling the speed of the vehicle, and the servo, which steers the vehicle. Thank you for watching our video. We hope you liked it.
On behalf of my colleagues, I'd like to thank Texas Instruments for giving us a platform to demonstrate our project.
We would also like to thank our mentor, Dr. Srinivasan, for his guidance and support.
Thank you for watching.
Thank you.